for this. There we go. Okay, so what we're going to talk about today is the cubic formula and make some connections with it. Now, here is an old this dates back from high school, right? This is, a big bang to people, your friends like all shivered over this when you did this in high school. This is the quadratic, we want to find roots of this quadratic equation. Notice that I'm assuming that my lead coefficient is 1, and that's cool because as long as the lead term is not 0, I can just divide through by it, right? So there's no real change in what the solution is here. Now, of course, we've got the quadratic formula, but where did they come from? Anybody remember what technique we did? What was it called?
Completing the square.
Yeah, complete the square. And you did something like you wrote, okay, x squared plus ax. And then you made this a perfect square by adding 1/2 of the squared. And this becomes right. And this was the whole trick because then really what you did is you rewrote this as u squared equals lambda, right? Where this bit is u, right? And lambda is just this mess taken over the other side, right? And so now you've got an equation that's much simpler looking than this. You take the square root, and what's the answer? U equals plus or minus the square root of lambda. Right? And then you went back and you built the formula, right? But really, this was the key step, is just taking the square root to get the answer, right? Now let's suppose you want to solve this. Now I'm going to do this kind of from scratch, but I'm going to do this by making like some kind of guesses at what the solution should be, kind of based on symmetry here, right? The first thing is just like before, I can assume that the leading coefficient of x cubed is 1, right? Because if it was something else, I would have just divided out by it and be done with it. And this time I want to do a trick that's similar to completing the square that will make this thing look a little bit easier, right? So let us let x equal u minus a over whatever this thing is, I'll take a third of it, right? And all this is going to do is this is going to give me another cubic, but it's going to be a little streamlined and be one that I can work with a little bit better. Notice that if I do this, then x squared is u squared minus 2/3 a plus 1/9 a squared. Right? And this cube, I think you better watch me on this, is u cubed minus, that should be a u squared plus a squared over 3u minus a cubed over 27. Right? Looks like I've made it worse because, well, maybe I have, but there's always, the bad before the good. So let's substitute in here. If we do the substitution here, I'm going to replace this by u cubed minus a u squared plus a squared over 3u minus a cubed over 27. And then a times x squared, well, that's going to be a u squared minus 2/3 a squared u. Right. Yes, I'm sorry. There should be a u here as well. And finally, plus 1/9 a cubed. And then what do I get? I get a b times x, so that's going to be bu minus ab over 3, and then I'm going to get my c. Now, when I put this all together, this is most triumphant because those two are dead. And I get u cubed. And what's left here, this is going to be minus, well, it's going to be u times something. It's going to be minus 1/3 a squared plus b. And then I'm going to get just this unholy constant term, which is going to be 2/27 a cubed minus 1/3 ab plus c is equal to 0. Everybody okay with that? And this is a little bit similar to completing the square. It's not quite as fantastic as this, where you lost everything. You've got this very simple equation, but you do get one that's simpler. And so the upshot of this is, if I'm going to solve a general cubic equation, this substitution right here allows me to change the cubic into a much simpler form that looks like this. Where A and B are these unholy messes, right? So if I've got this licked, then I won the fight. Everybody okay with it? Now, let's go back to the quadratic again. Once we did our most triumphant change of variables and got down to here, what do? Well, we got two roots that involve the square root of this. And we got a plus solution and the minus solution, right? And what's interesting about plus or minus, they are the square roots of unity. Those are the two numbers that you can square and you get 1. Now I'm gonna try to take advantage of that little insight as follows. Plus or minus 1 are square roots of unity. So what's the analog? What are the cubic roots of unity? And I'm gonna try to use those cubic roots of unity to guess at a solution for the cubic. Naturally, we can figure this out pretty quick. I mean, if I know one answer to that, right? 1's one of them. And that factors that way. This one, of course, corresponds to our silly solution 1, and this corresponds to the happy fun solutions, right? Which are if you get on your horse and ride, take either one of those roots, plus or minus, and you cube it, and do all of you get 1. Right? No surprise, because it's only that equation. So I am going to define omega is, I'm going to take a positive 1. And before I stampede off, I'm going to note some important properties of these little animals. Let me make a couple of observations. Multiply this out. So it's -1 plus square root -3/2. Because omega squared is -1 minus square root. I mean, just multiply that out. And that's what you want to And this is the same thing as the complex conjugate. Right, you all remember what complex conjugate is, right? So notice you just change the sign of the imaginary part. All right. And let me make one more note that'll be useful to us. That's kind of sexy right there, because what that means is that's one of the cube roots of unity. That's another one, and that's the silly one. When you add them up, you get 0. And this follows actually from this right here. Right. So in particular, when you add these two roots, you get -1. Right? When you add the two ones that are not silly, you get -1. Okay, so what's the inspiration here? The inspiration is as follows. In the original quadratic case, you got two roots, you got a square root, and they vary by square roots of unity. What's the analog here? Well, this is art. Well, let's assume has 3 roots. And let's assume that they take on this form here. I'm going to write them this way because it's convenient. Let's assume that one of them, by the way, let me point out, so here's a blast from calculus. If you have any cubic polynomial, then you're guaranteed to have one real root, right? Maybe more, but there has to be at least one, and that follows from the fact that this is a continuous function and it goes to infinity. Well, actually, since the leading term is positive here, we go to infinity to the right and negative infinity to the left, so it has to, by the intermediate value thing across the axis. Assume that we can write this as 2 numbers here, hopefully real numbers, but we'll see. That's my best guess is what the plus or minus analog is for 3 things. The root, and then you sort of spread the other roots of cube root of unity across this like this. Now, let's see what this gets us if we make this assumption. Notice that x cubed notice that x cubed is x minus r1, x minus r2, x minus r2. Right? Because there's the 3 roots, right? Now, let me do something boring. If you multiply this out, of course you get an x cubed, and that's the only way to do it. And then x squared terms, well, you pick these 2, then you got minus r3, you pick these 2 minus r2, pick these 2 minus r1. So basically the sum of the roots is the coefficient of the x squared term. The coefficient of the linear term, you pick these 2, or you pick x and these 2, or that x and these 2. So it's basically the sum of all 2 products. And then finally, everybody okay with that? Now, I know that these must, I'm going to match here, but let's go off of our solutions here and see what we get. So what we want here, let's sort of check this out and see what these get us, given our assumptions here, the assumed solution. Well, notice that R1 A plus B, R2 is omega A plus omega bar B, and omega 3 is omega bar A, omega B. That's the order I did these right. Notice, and this is a great sign. Add this, and you get R1 plus R2 plus R3. And you get A times 1 plus omega bar plus B times same business. And what does 1 plus omega bar add up to? 0. This is a really good sign, and this means that I was sagacious in picking it this way. And this is what it should be because I have no quadratic terms, right? So the only thing that I've done, that was just a confidence builder, right? I haven't really accomplished anything except, you know, breaking my arm, patting myself on the back, but you know, so far so good. All right. Okay, let's push this another step here and see what we can get. Let's look at the next term. And to do this, I think I should collect some things. The first thing I'm going to do is I'm going to multiply these out. This is going to be, it's not terrible. R1 times R2. Well, that's going to be omega A squared plus omega bar AB plus omega AB bar B squared. Y'all guys watch this. But everybody okay so far? The product of these two is similar. This is omega bar A squared plus omega AB plus omega bar AB plus omega B squared. Okay, so far. And this is the most obnoxious one, but it's not too bad because actually this is omega times omega bar A squared. First term. And what's omega times omega bar?
Modulus of omega.
Right, which is 1.
Okay.
Right. So this is omega times omega bar is 1. So this is A squared. This is omega squared AB plus omega bar squared AB plus, again with the 1. But omega squared and omega bar squared is omega bar squared is omega. Everybody okay so far? Now, let's see what we get when we add these up. When we add these up, this is what symmetry will value. You get A squared, 1 plus omega bar, and you get B squared times 1 plus omega bar. So those two are going to vanish, right? Because again, these things are 0, right? But we've got this whole orgy of things in the middle here. We've got to sort out. And so I've got omega plus omega bar AB. And I've got it 3 times. Everybody agree with that assessment situation? And lucky me, what is omega plus omega bar? It's -1, right? So this is -3 AB. And it's also equal to this. It's also equal to A. Right? So my first equation that I can get is A. Is this. Because remember, this thing is the coefficient of X, which must match A. Okie dokie. All right. So this is the first big piece right here. The second piece is, let's look at R1, R2, R3. Well, I already know what R2, R3 is. So R1 is A plus B. So there's my R1 bit. And R2, R3 is this. Now let's see what comes out of this. This comes to be A cubed plus omega bar A squared B plus omega A squared B plus AB squared, and then B through here. So I get plus A squared B plus omega bar AB squared plus omega AB squared plus B cubed, which looks awful until I look a little closer. At least I hope it's all a little closer. Let's look at the A squared B's. What does that bit add up to? That's a zero because it's A squared B times the sum of all the roots. And if you look at, oh, I'm sorry, I underlined the wrong one, didn't I? Right, okay. I see, so let's do this. There, those three, I add up to zero. And these three add up to zero. So this is the much more harmless looking A cubed plus B cubed. And what does this equal? Almost. It's actually negative B, I think. Right, because negative this is equal to B, so R1, R2, R3 is negative. So let's see what we get out of this. We now have a couple of equations. One of them is, actually, let's do it this way. 3AB negative A and A cubed B cubed is equal to negative B. Great. And before I stand feet off, let me see if I agree with my equations. And I do. Okay. Looks awful, doesn't it? But there is a good strategy for solving this. Let us write B is negative A over 3A. And now let's see what happens. Let's put this back into this equation. And what I'm going to get is, I almost keep saying this up, it's getting kind of exciting here, because what I get is A cubed plus B cubed. Well, B is now negative capital A cubed over what, 27 B cubed? Oh, it's A cubed, yeah. There we go. That was the whole point, was root of B is equal to negative B. And so, multiply by A cubed, I get A6 plus BA cubed minus A cubed over 27. 0. So I'll do a little kind of change around. A6, I get a minus BA cubed over here, so bring it over. So it's going to be BA cubed, and then that's going to be minus A cubed over 27. And what an idiot I am, right? I mean, how much can I screw up here, right? I start off with a cubic and then I end up with a 6-degree polynomial. I mean, that's gotta be like the worst case ever. However, there's something very special about this. What can we do here? Quadratic. This is actually quadratic in the variable a cubed, right? And so what I can do is solve this just like it was a quadratic. And in fact, what I get is I get a cubed is equal to negative b plus or minus the square root of b squared minus 4 times this times this. So that's going to be plus 4 a cubed over 27 all over 2. Everybody agree? Now, you may worry a little bit about which root you pick. So what you get is, so you can solve this completely. A is now, again, you might worry a little bit about what root you pick, but it actually doesn't matter because, and you can check versus these identities to see that this works, but I will pick A to be positive, negative B plus square root of B squared plus 4 a cubed over 27 all over 2. And it turns out B, its companion, you can use either one of these to figure out that in fact B is the other root. So if I picked A to be the negative, B will be the positive. If I picked A to be positive, B will be the negative.
Minus, yeah, minus.
And I forgot to put the negative. Right. Everybody okay? So here are my roots. Right, so here are my roots. One root is the cube root of negative b, actually you're this way, plus square root of b squared plus 4a cubed over 27 over 2 plus the cube root of negative b over 2 minus the square root of b squared plus 4a cubed over 27. And for the other roots, one of the other roots, multiply this by omega and this by omega bar. And for R3, multiply this by omega bar and this by omega. And that will give you the 3 roots. So there it is from scratch. I have never had the guts to do the 4th degree polynomial because actually the 4th degree takes too long because you actually need to solve the 3rd degree first, which is awful. However, for your consideration, I'm going to focus on this root, but it doesn't matter. This is one of the roots anyway. Let's look at some special cases. So I'll leave my solution over there. What if I give you this? Let's start off with this warm up here. Let's look at the following cubic polynomial. Suppose I have to solve this. you are so powerful and mighty now because you have the cubic formula, but there's a better way to solve this one. Does anybody see an easy solution to this? One works. Everybody agree with that? If you shove one in there, it balances, it's good. So that means that this polynomial has a factor of x minus one, right? And so you can use that to get all the solutions. This should be something like x squared plus x plus 4, something like that. And so, well, one solution is or you get these two complex solutions to this. That's not right. What am I? -15. Right. You get these two other ones that are complex conjugate pairs, right? But this formula should work anyway, shouldn't it? Right? Even though I'd be silly to do it, but let's try it because I am that much of a masochist. So in this case, what we have is we have A is equal to A is equal to 3 and B is equal to -4. So let me figure out what this awful thing is that's under that nested radical. So B squared minus 4/27 cubed. Well, so that should be what, 16? And then A cubed is actually 27, which is convenient. So this is 12, isn't it?
You want minus or plus?
I probably want plus there, don't I? Yeah. I'm glad you got me. Yeah, because it should be 20. Good, that's better. Everybody okay with that? So that's what goes under the radical. So in this case, my pieces are this. Well, so A should be the cube root of negative B, which is 4/2. So that's going to be 2. And this is the square root of 20. Well, in fact, I would trust the root down. And plus the cube root of 2 minus the square root of 20/2. And of course, that's like 2 radical 5. So root of 2 plus radical 5 plus cube root 2 minus radical 5. Now, I don't know much, but I do know that that is a real number. Do I agree with that? Because 2 plus radical 5, 2 minus radical 5, these are both real numbers. And if I can take a cube root of the number, whether it's positive or negative, it's a real number. There's only one real solution to this. That's one. The other two are complex conjugates. You may not have ever seen that identity before. But if you take the cube root of 2 plus radical 5 and add the cube root of 2 minus radical 5, you will get 1. I promise you, or your calculator broke it. Right. Now, let's do another one. I'm going to do kind of a two-part of this one. This one is specifically designed for growing young minds to make you angry. Here's one right here. Let's do another one. Here, I want, yes, indeed, x cubed minus 21x. Let's extract roots of that. Now this one's got a little twist to it. Right. Okay, once again, use the formula, and as you might guess, since this is a math club talk about the given formula, we're going to use it. But does anybody see an easy route to this one? One also works on this one as well, right? I mean, I'm going back to well on this. But this time something different will happen when I split it up. Piece here. This should be x squared plus x minus 20, I guess. Agreed? This one, well, if you look at the quadratic formula, what goes into the radical is going to be positive this time. So this has got a pair of real roots too. And in fact, this factors nicely as well. So actually, this thing is just this polynomial, right? So here are the roots. They are 1, 4, and -5. Everybody agree with that assessment? Okay. Let's run the formula. So here we have A is -21 and B is 20. Right? So again, let's figure out what this awful thing is under the radical. Right. This is going to be 400. And A is 21. Well, that's 7 times 3. So when you cube the 3 out, it's going to cancel that. So this is going to be 4 times -7 cubed. And that is 1,372 minus 972, which is -18 squared times 3. Right. So the upshot is that what this formula gives us, so here we have square root of b squared plus 427a cubed is equal to the square root of this thing. So it's going to be, this is 18i radical 3. Agreed? Square root of that. And the I, of course, is for the square root of -1. So let's go back to the well with our formula here. Let's see, -b/2, that's going to be -10. Agreed. And this garbage divided by 2 is going to be 9i radical 3. So this is going to be that has to be one of those 3 roots. Which one is it? Definitely silence falls over the crowd.
Always guess 1 and 0.
Actually, the weirdness about this one is, let's see if we can, let's think about this for a minute, and see if we can figure this out. Of course, this is just death on a hot plate here, right? Because it's square root of some complex number, right? So I think this part of the top is going to turn into a little bit of a lie, because I said high school, if you went to a really good high school, how many of you have ever worked with complex numbers, done the vectors and taken, messed with the angles? Okay, well, that'll be good enough. Forget the cube root. If I were to draw this thing in the complex plane, before that, so let me draw a little picture here. Perhaps not the greatest scale. 2 colors. So if I have -10 and then 9 radical 3, I mean, who knows what that is? That's like 15 maybe. So -10, so this looks like this maybe. And -10 minus like this. So this would probably be the point -10 plus 9i radical 3. And this would be -10 minus 9i radical 3. Okay, that's what both of these look like in the raw. Essentially. Before I've taken the cube root. Effectively, what's the cube root going to do? Right, it's gonna squeeze this angle into about 1/3 of what it was. Right, so if I take the 1/3 power here. Like this. And of course, it's going to shorten it up. Everybody agree with that? And if I take the 1/3 power, it's going to be symmetric here. Right? Everybody agree? Now, actually, this makes me feel a whole lot better because now it's sort of plausible that this cube root plus this cube root is a real number, isn't it? Right? Because what's going to happen when I take this complex number and this complex number and add them up, right? It's going to basically, it's going to kill the imaginary part. And it's basically going to take this length right here and double it. Everybody agree with me? Anybody want to guess which one it is now? That's a good guess. Yeah, it is 4, right? It's a little too long to be 1, and it's sure pointing in the wrong direction to be -5, right? However, you could get 1 and -5 by mucking around with this, by putting an omega here and an omega bar here, or the opposite order. Everybody agree with that? And so you can also figure out something here, and that is what is the sum of these two complex numbers? Well, it should be 4. We've kind of figured that out. Let's call this, we call this theta. This should be correct, right? Because this length right here, I'm going to call this x. This is 2 times, I'm sorry, that's bad. We'll call this r. Right. So if this red length is r, then the cosine of theta just is x coordinate, and you double down on it to get what the actual length is. Everybody good with that? And so you can actually write down what this is. So this is actually radical 7 times the cosine of 1/3 of pi minus inverse tangent of 9 radical 3 over 10. Now that's probably another identity that I'm willing to bet that you've never seen, but check it, run it on your calculator. If you take the inverse tangent of this thing, subtract it off the pi, take 1/3 of that, the cosine, multiply by radical 7, you will get 2. Right? And that's a nice consequence of this. And I've always found it kind of fascinating about how these numbers kind of relate like that. Okay. Any questions? Let me sort of give you a push here. So here's my final comment. If you like this, and if you want to go out and take advantage of your friends who aren't math majors and win bar bets with this, let me point out that you can make all kinds of things out of this technique. So for example, let me point out that if R is any real number, then 1 is a root x cubed plus rx minus r plus 1, right? Because we plug in x equals 1, this works. So you can put any real number in there you want, square root of 2, 87, whatever you like. This polynomial will have root 1, and it will also have this thing. So if you want to make things that, you know, nobody's ever going to guess, you can do this. And one's not special. You can adjust this to make this anything you want. So for example, if I wanted to build a polynomial of that form that had root 2, I could look at something like x cubed plus 7x. Well, I want to have root 2, and this comes to 8 and 14. So let's subtract 22. That has root 2. Run the formula and see what kind of weirdness you get. So anyway, any questions on that? Any questions? Well, maybe next time I'll have the guts to do quartic, although it's infinitely worse. And I don't know if everybody's familiar with this, but there is a nice radical formula that I left on the board up here for cubics. There's also, if you look hard enough, you can even find it in some books, there is a solution to quartic equations, but there is no solution to 5th degree and higher equations in general in terms of radicals. Some fifth degree polynomials you can solve with radicals. That means by using sums, products, quotients, differences, and only the symbol square root, cube root, fourth root. There are some 5th degree polynomials like this one. This one right here. Oh, actually, I better check that. Yeah, I'm pretty sure this one right here probably cannot be solvable. I'd have to check the Galois group, but anyway, you cannot solve 5th degree and higher in general, only in certain specific cases. So, of course, that doesn't mean they don't have solutions. It just means you can't write them in that particular form. Okay, any questions? Yes.
What's a Galois group?
A Galois group is
Jeopardy question.
What the Galois group is you're solving these in a field, right? So you're solving these in a mathematical structure like the rationals or the reals or the complex numbers, where you can add, subtract, multiply, and divide as long as you don't divide by 0. The Galois group is of a field extension over a smaller one. Is basically the group of homomorphisms of that extension. So it's maps that are one-to-one and onto and preserve the structure of the field that fix the bottom field. And these form a group just under function composition. They're all invertible because they're all one-to-one and onto. And this group tells you a lot about roots of polynomials, right? And so if Galois groups, if these groups of automorphisms have certain properties, then the polynomials that generate that field extension have certain properties of the roots. Basically, it measures sort of symmetries. So I'll give you a simple example. And this maybe it's an oversimplification, so if you're really curious, we can take it further. But if you have irrational numbers, right? Suppose you have the polynomial f of x is x squared minus 2. This has no roots in the rational numbers, right? But it does have roots in this field. This is the smallest field that contains the rational numbers and the square root. Now, this field, this is basically all ordered pairs look like this. There are two, what we call automorphisms in this field. That is a function from this field to itself that is one-to-one and onto, and it preserves the field structure. One of them is the other, right? No shock there, right? The other one, remember back when you were in high school and your teacher always said, oh, rationalize that denominator, right? And you'd have to multiply by the time you get, that's what it is. Yeah, they probably didn't say it. The teacher got one group properly. Anyway, this is the other one. And notice that this corresponds to the two roots of this, plus and minus radical 2. Basically, what this does is it shifts these roots, right? Radical 2 is one root, minus radical 2. And of course, if you have the cubic equation, it gets more and more complicated. For example, there are some cubic equations that have 3 real roots, and the Galois group, it just permutes those 3 roots. There's some that are more complicated. If you've got complex conjugation, it fixes one and swaps the other, and so forth. So anyway, it's an interesting algebraic object that is studied quite a lot and has a lot of sort of consequences in solving polynomial equations. Other questions? That was a very rich question. We could spend days on that one. That's right. These former students of mine, I mean, they're big therapy bills for the month. Yes.
What's your biggest bar bet win here?
I'm more of a teammate, right? I like set the ball in motion and watch it play out. You know, that's kind of my thing.
So bet C7 won anybody.
He says things and other people start fighting about it.
That's right. Other questions? All right. Well, thank you all for turning out, and I hope you have a great weekend. Think about the Math for All conference next week. It should be a good thing, and there'll be even more pizza than usual next week. So, also remember there is an important rule of Math Club, and that is no pizza is left untouched. That sounds kind of gross. But anyway, you all are starving students, so the pizza should be gone. Take it home, whatever it takes. Oh, any questions out there? Okay, y'all have a good week, and we will catch you on the flip side.